Hello, everyone, and welcome to our talk. In September 2019, we finished migrating Wikipedia and its sister projects to PHP 7. This is a story of how we made it possible. I'm Effie. I studied physics and scientific computing, only to fulfill my childhood dream of becoming a sysadmin. I have worked in various small companies, a really dead multiplayer game, and for the last 2 years, I've been an SRE at the Wikimedia Foundation.
Hello, I'm Giuseppe. I also studied both physics and Fortran, which is what Effie meant by scientific computing. I spent the last 6 years as an SRE for your favorite PHP-powered encyclopedia.
In this talk, we'll discuss how we run a year-long migration on Wikipedia without most of you noticing. We know that many find PHP less than exciting. The fact is, though, it powers many websites you visit every day, including Wikipedia. This project was led by SRE and was an effort of SRE and engineers from different teams across our organization, from other Wikimedia chapters, as well as our very dear volunteers. During this talk, we will briefly go through our infrastructure, explain the reasons behind the migration, discuss our challenges and our migration plan, go over our testing and production techniques and the rollout process, talk about some of the issues we had and how we tackled them, and close with our new journey to migrating our main application to Kubernetes. The Wikimedia Foundation runs the infrastructure of Wikipedia and its sister projects. It's a non-profit organization which has no affiliation with other websites bearing the Wiki prefix. All hosted content is managed by volunteers, and we have some really bizarre pages like extreme ironing, possible explanations why unusual food tastes like chicken, and a 10,000-word talk page about aluminium versus aluminum. Occasionally, Wikipedia becomes a subject of censorship, and sadly, despite many efforts, the Wikipedia ban in China still stands. Wikimedia also supports many other projects like Wikiquote, Wikinews, Wikiversity, and of course Wikidata. Wikidata is a project run by Wikimedia Deutschland and is the central storage for the structured data of Wikipedia and sister projects. According to Wikipedia, in January 2021, Wikipedia will be turning 20. It began as a complementary project for another online encyclopedia in January 2001 to allow collaboration on articles before being peer-reviewed. During its first decade, Wikipedia saw its first 10 million articles, and with Michael Jackson's death, its first celebrity-related outage. In its second decade, it became one of the most popular websites on the internet. The third decade finds Wikipedia in a battle against misinformation and disinformation in everything from a global pandemic to the roundness of the Earth. Over the years, Wikipedia has not only evolved to a movement about free knowledge, but also to a reliable source of fact. Before we start, we shall go through a quick and simplified overview of our production in 2017, so you can see which parts were affected by this migration and how this fits the bigger picture. Our infrastructure runs on open source software, so everything we mention here, even in-house developed software, is freely available online. We have 2 primary data centers in the United States and 3 caching points in San Francisco, Amsterdam, and Singapore. With the magic of GeoDNS, we always try to route you to the nearest operational data center. We are currently serving about 22 billion page views and about 55 million edits per month, with a little over 1,300 bare metal servers and a team of 27 SREs. Now you may wonder why we're not using the cloud. Well, we want to have full control over who can access our data, and then at least at this traffic level, it is cheaper to own your infrastructure. And lastly, when this project started, there was no cloud. If you look at our infrastructure from far away, it's nothing more than your typical web architecture. In 2017, our edge caches were running Varnish. Apache is the web server in front of our application, and we're using HHVM as the execution engine for MediaWiki, our core application. The core component of our edge caches was Varnish. Around 90% of our requests are cache hits. Thus, these requests terminate in the caching layer. The caching layer itself is divided into two components: text for static text objects like CSS and HTML, and upload for media objects like images and videos. Moreover, the varnish frontends store objects in memory, so this is where we find the most hotter objects, while the varnish backends store objects on disk. Our core application is MediaWiki, a 19-year-old Apache PHP MySQL application, and around MediaWiki there is a very thick layer of caching. In other words, when you're requesting an article, we will first check the caches on varnish front and varnish back. If we get a miss, you will hit MediaWiki, which will look for a rendered version of the article, initially on Memcache, and if it's not found there, in a MariaDB database cluster called parser cache. On a miss, you leave MediaWiki without any other option than to render the article and serve it back to you. Moreover, when you're editing an article or uploading media, you're again interacting with MediaWiki. So it's the most important part of our infrastructure. Of course, MediaWiki itself is surrounded by many microservices like Parsoid for parsing, Thumbor for thumbnails, Mathoid for rendering math formulas, etc. We have three clusters that run MediaWiki. The app servers for web requests, the API for API, and the job runners for running async jobs like video encoding. Now, in 2017, the MediaWiki code was executed by HHVM. The hip-hop virtual machine is a PHP and Hack execution engine by Facebook, and it is to PHP what JVM is to Java. It converts PHP code into bytecode, and then this code is in turn translated into machine code, and then it's executed. The reason we switched to HHVM in 2014 was simply that it performed better. Over time, we learned to manage HHVM weaknesses, and we were happy with its strengths. It allowed us to reduce our resource utilization of our clusters while cutting down the latency of the edit path by more than half. And life was good.
Well, it was good until September 18th, 2017, when Facebook announced that future versions of HHVM would focus on support of their own PHP-derived language, which is called Hack, and drop PHP 5 support. Most notably, given Hack and PHP 7 are both evolutions of PHP 5, but in somewhat different directions, Facebook decided to just drop compatibility with traditional PHP engines and concentrate efforts on what Facebook itself was using, which is surely a reasonable choice from an engineering point of view, but left us with a hard choice to make. Anyways, after learning the news, we started discussing the best course of action. It would have been relatively easy for us to evolve our code base to just use Hack, but MediaWiki is free software and has a very large third-party install base, overwhelmingly using PHP and not HHVM. Now, being good free software citizens, we wanted to avoid forcing our user base to perform a dangerous and costly infrastructure migration to HHVM. So we started discussing the potential road ahead in a public RFC. We were determined to get away from using Apache mod.php that we used before we migrated to the HHVM, and use an application server for PHP 7 as well. That application server is PHP-FPM, which stands for PHP Fast CGI Process Manager. PHP-FPM enables PHP scripts to make better use of server resources without the additional overhead of running them inside a web server. And most notably, PHP-FPM can reuse worker processes repeatedly instead of having to create and terminate one of them for every single web request. Also, since we last used PHP 5, a more efficient code caching system called opcache was created, which would store the precompiled bytecode for PHP scripts in memory. With all those improvements, PHP had supposedly cached up in terms of performance with HHVM. And indeed, our main worry was about performance. As Effie said before, we shipped about half of the latency that we had on the edit path moving to HHVM, and we could not give that up when we switching back to PHP 7. Early tests were very promising, though. PHP-7 would guarantee a 20% better performance than HHVM when parsing wiki text in a micro benchmark, meaning we had a fighting chance. This doesn't mean that we didn't have a very steep road ahead. We were facing a double migration from both PHP5 to PHP7 and from HHVM to PHP-FPM, while serving 100,000 requests per second and 17 billion page views per month. Insert here your best joke about fixing your plane while flying. So the decision was made. We were set out to start the migration, and doing so didn't come without challenges in terms of functionality, performance, and observability. First of all, some subtle behavior we don't catch in our code testing, which is not great as MediaWiki is quite an old software, could cause bugs in production. We'll see some examples of that later. Also, we do set limits on how much resources rendering a wiki page can use in terms of wall clock time, memory, and CPU usage. As you would probably expect, given we accept literally any edit from anyone. Editors have become very good at optimizing their edits to keep any very large page on the edge of those limits. But now we're changing the rendering engine. And changing the rendering engine changes how resource utilization is accounted for. And we might end up having pages that exceed those limits in PHP-7, and those will be unable to be rendered, while rendering perfectly OK under HHVM. Then, of course, there is the question about performance. Up to now, we just had anecdotal evidence that PHP-FPM would perform well, right? How about under production load? What blind spots we didn't catch with just running a micro benchmark? Will we need to expand our server fleet? Did we constantly optimize our code paths for HHVM over the last few years without even knowing? And the last problem we had was even sneakier. HHVM has been built with observability as a centerpiece. And we were able to extract a flurry of metrics and profiling information from HHVM. We could only gather a different, smaller set of data from PHP-FPM, and most notably, we didn't have the ability to extract profiling data at runtime from it, without severely impacting its performance. This generated big questions regarding our ability to debug production issues with the same ease that we had before. As for any migration, we set our goals early, and they were pretty simple. Almost no one should notice that we switched to PHP-FPM. Latency, error rate, and resource utilization should stay more or less the same. All of our application cluster run Apache and HHVM. Our first step was to install PHP-FPM alongside them on every server. So our setup would have HHVM continuing to listen on localhost on port 9000, PHP-FPM listening on a Unix socket, and Apache proxying request to either engine, depending on the value of a cookie, falling back to HHVM if no cookie was present. Before starting to actually send users to PHP-FPM, we needed to be able to measure our goals, which meant that we need to tag all log messages coming from either PHP-FPM or HHVM, adding a rendering engine dimension to our rate error duration time series, creating a PHP extension that bridges some of the observability and functionality gaps in PHP-FPM. I'll tell you more about that later. So now that we were all set, we had a functional setup, and it was time for some accurate benchmarking. First of all, we tested rendering on our production infrastructure, the Barack Obama English Wikipedia page, which is particularly expensive to render, with either PHP-FPM or HHVM. Results were actually really promising, as you can see from the graph here. At any concurrency we tested, PHP-FPM would outperform HHVM, as you can see, both in terms of median latency and of 95th percentile. We were very happy, but this test was kind of cheating. When we render any page, we make ample use of application layer caching for things like parsing wiki text to HTML. What would happen when not a lot of requests would be able to use such cache? Well, we found out, we did a test disabling caches rendering the Australia English Wikipedia page, and we found out that when performing such heavy computational heavy payloads, HHVM would actually outperform PHP-FPM, especially as the concurrency increased. This underlined the risk of being much more dependent on our application layer cache like MinCached than we were before, and some potential dangers whenever we had to operate with relatively cold caches, for instance, when switching traffic from one data center to another. We consider these risks acceptable, though, and we moved on. This set of tests proves, again, that benchmarks, especially simple ones, usually miss a lot of nuance and don't give you the full context. Anyways, this also holds true for these benchmarks that I just showed you, right?
At this point, we're ready to actually open the dams of production traffic to PHP-FPM and test it in a real-world setting. PHP-FPM was installed and ready. We had means to observe how it is behaving, compare it, and debug it. Our internal tests were encouraging, and we had a testing strategy that was respectful to our users. Testing in production sounded a bit unprofessional a few years ago, but now it is safe to say it is the norm. As a user, hitting the testing production jackpot might not be always pleasant, but as an engineer, it is one of the best tricks in your bag. We test in production for the same reasons everyone does. Our traffic level is almost impossible to replicate, and no matter how much testing we can do and how much time we invest in it, we can never replicate all the bizarre ways users find to break production. We constantly use multiple techniques. Depending on what we are testing as we see fit. For example, we use canarying for infrastructure changes, like upgrading our edge caches or tuning our TLS parameters without making the site inaccessible to some users. For new features like a new media player, we A/B test and we let users opt in or opt out. For our weekly application updates, we run the MediaWiki train, which leaves a station for small wikis on Tuesdays. If no serious regressions are noticed, we move to the larger ones on Wednesdays, like Commons and Wikidata. And then, given the larger scale, a good chunk of issues are usually found at this point, including the most potential scalability problems. Finally, it reaches the English Wikipedia on Thursdays. But apart from the traditional testing techniques, we have one more ace up our sleeves, and that is our trusting the volunteers. The volunteers that donate their time to Wikipedia, either by managing content or writing code, have created a community around us. And that community is valuable to SREs as they will report any issues, and sometimes they will also help us fix them. That gives us an advantage when it comes to testing in production. Of course, there were several ground rules, but the important ones were to keep the blast radius to a minimum and affect as few users as possible. Then we wanted to be able to easily switch from one rendering engine to the other, both to compare, but also to revert if things go south. Then we wanted to have a toolbox ready to look into issues as they arise. And lastly, users initially should knowingly join this experiment. Like Giuseppe mentioned, we were routing traffic using a cookie as an on-off switch. The presence or absence of the cookie would help us to have requests being consistently served by either rendering engine. Initially, we started with manual tests. Generally speaking, our go-to way to manually test is our debug service. We craft requests with special headers which bypass our edge caches and are routed to our debug service on demand. So we executed tests which we could thoroughly inspect. Then we continued with the Wikimedia Debug browser extension to elevate our visual testing. Wikimedia Debug is a browser extension for Chrome and for Firefox, and it's our number one help when we are testing in production. Using the extensions menu from our own browser, we can route requests to servers, we can add experimental features like the PHP-7 cookie, and profile requests on demand. As we said, our project strength is their community, which is frequently involved in the improvement of our infrastructure. So, logged-in users were thus given the option to opt in to the beta feature of seeing sites rendered by PHP-7. Reaching out to our community resulted to about 10,000 English Wikipedia users opting in the beta, which resulted in several and very useful bug reports. Now, let's say that a user bears the PHP 7 cookie. What happens next? Two things. One, the request is routed to the appropriate cache lot. Varnish, our caching proxy, looks for the requested URL in its PHP 7 cache lot. As we mentioned before, that a bit over 90% of our requests are served by our cache. And that being said, we wanted to avoid the cache being polluted by poorly PHP 7 pages from the beta users. HHVM users should get HHVM rendered pages, and PHP 7 users should get PHP 7 rendered ones. But more important, we wanted the ability to shut down traffic to PHP-FPM without needing to do an expensive and complex mass cache invalidation. And we achieved that by setting the X7 header and using it in conjunction with the var header. Now, and two, after a request is forwarded to Apache, Apache will route the request to PHP-FPM if the relevant cookie is present. This is a more visual representation of what we discussed in this section and the one before it. For almost 1 year, our production was split in two. It was in a transitional state where some incoming requests were routed to HHVM and some were routed to PHP-FPM. However, logged-in traffic represents roughly 5% of our total traffic, so it was time to extend this experiment a bit and widen its blast radius. Extending our tests mean that we started setting the cookie to random users based on some calculations done on the client and the server side. We added in an application variable where we could control the probability of a user getting the PHP-7 cookie, which would expire after a week. With that setting, we could say, for instance, that 0.1% of our anonymous users are being served by PHP-7. Of course, this wasn't entirely true, since not all the users or devices accessing our application servers were accepting cookies. The advantage here was that we could roll back and roll out users in a matter of minutes. Pushing more traffic allowed us also to do some more fine-tuning, like bumping up PHP-related caches or increase the number of workers. But of course, we ran into some troubling issues too. We were experiencing some memory corruptions, which we overcame by placing various workarounds and restarts, because everyone restarts, and then finding that PHP-FPM suffers when it reaches its max workers, which was a minor defeat that we had seen coming during our initial tests. We accepted that we will rely more on our application caches than before and work towards optimizing them. Giuseppe alluded to this already, but I will expand it a bit. We periodically switch between our primary data centers, and during a switch, the caches of the target data center were cold. HHVM worked extra hard, and we got away with just a few scratches, but without an outage. In a similar scenario, with PHP-FPM, we would probably have ended up with our sites becoming unavailable. We then gradually started giving away PHP-7 cookies to an increasing number of users, up to 50%. Looking at the commit history, we had a few back and forths, as in general we tend to err on the side of caution. It is easier to roll back anyway first and ask questions later. To conclude, this process was completed in a span of 5 months, during which the question, "Is it PHP-7?" was asked dozens of times. The last commit of the series in September 2019 expresses how we felt at the time. Of the 5 stages of migrating to PHP-7, I hope this is acceptance. And indeed, given that there were no other reverts in our later commit history, we accepted that this part of the migration was over and successful. The work was not done, though. This was about 50% of our traffic served by PHP-7. There were still many clients that do not accept or store cookies. Most of that cookieless traffic goes to the MediaWiki API. The API servers are a separate cluster of servers, but share the same configuration. Left unable to convert most of this traffic in a consistent where using cookie data, we resorted to converting a percentage of this traffic. To do so, we started converting our API servers to only run PHP-FPM. We are using Puppet to provision our server, so we introduced a server feature called PHP-7 only. Given that each API server serves about 2% of API traffic, we had a rough estimate of the amount of traffic we are pushing through PHP-7. This process went very well, and at the end we had migrated 100% of our live traffic. Mission accomplished? Well, not just yet. As every self-respecting transition in a complex environment, you can't really claim victory until you've solved all the additional use cases that are very important but not immediately user-facing. For us, those were jobs. So we had to migrate the job runners, a cluster of servers dedicated to running a few dozen different asynchronous jobs MediaWiki can schedule, which can be used for different things like sending notification emails, invalidating URLs from the edge caches, encoding video, etc. After switching all jobs in our staging cluster, we moved to production. We started by switching the low traffic jobs one by one. Now, switching jobs and ensuring that everything was fine was a little bit trickier because a job could complete successfully, but not with the expected result. And it would take time for us to find out, and mostly through user reports. Additionally, we have jobs that run all the time, and we have jobs that run once or twice a week. After we migrated about 50% of the jobs to PHP-7, we switched the rest of them in one go. And at this point, we enabled the PHP-7 flag to all job runners. Our cron jobs were migrated in a similar way, and all that went surprisingly well that we know of. Now, even when our PHP-7 traffic was at 100% and all our jobs were migrated, we had to do the most boring part of every party, cleaning up. We had to go over all our repositories and start removing HHVM-related code and continue with reverting any transitional changes like splitting the caches, as well as cleaning up our Puppet code and removing HHVM traces from all our systems. This took some time as well, given how much our infrastructure code was tied to HHVM. On the other hand, it's surely hard to break something that is not there anymore. The last part of the sweeping was to polish our dashboards since they had been adapted during the transition to support both engines, and of course reinstall all our 150 servers. And even though our server installation is nicely automated, we couldn't do all of them at once.
You might remember I said earlier that we go over some of the issues we met while migrating. I'll just pick a few significant ones that we either solved or worked around. So first of all, I'm a big believer in choosing your battles. You can't assume you'll fix everything in the software by patching it, nor you can wait for a perfect solution for every issue you find. And sometimes this means you want to forward port a bug, at least temporarily. So the bug. Turns out that PHP and HHVM had mistakes in their Unicode tables for a very long time, meaning that some specific characters would be incorrectly capitalized by MB to upper, as you can see here in the slide. This in turn meant that when we saved some wiki titles with a wrong capitalization, now with fixing the Unicode tables that were introduced in PHP 7.2, the software wouldn't be able to look up the titles because capitalizing would result in a different letter. And the error was fixed. So our solution for the transition time was to add a special lookup table that we checked before calling MB to upper when capitalizing the title of an article, practically forward porting the bug until we were completely migrated and we could fix the data in the database. But this is not it, of course. We didn't just have bugs that we needed to forward port, but also HHVM-specific features that we came to rely on. For example, one of those is the ability to define pools of persistent connections for HTTP requests, thus avoiding to have to reestablish a TCP connection for every request you want to make. While the cost of establishing a TCP connection is usually negligible on a local network, it's not when you have to communicate across data centers, and encryption only makes the latency impact of establishing a connection for every request worse. As you can see from the diagram here, every connection requires 3 full round trips, and those latencies pile up quite fast. Now, PHP-FPM's curl extension had no such functionality as connection pooling, and we saw a huge performance hit for some requests to remote services, to the point that it could become a full blocker for our migration. Our solution was to start using a middleware to manage all communications between MediaWiki and the rest of production, Envoy proxy. The results were really amazing. Having a proxy establish and managing persistent connections to other services had improved our RPC performance by 40% over what HHVM could do. We've published a blog post describing the gains of having a middleware managing remote requests. You can see the link in the slide if you want to know more. So in this case, we worked around the limitation in PHP-FPM by using a supporting sidecar. But this approach doesn't always work. There are other cases where there are tools that we came to rely on. One of those was Xenon, which is an HHVM subsystem that would sample stack traces from all running requests and submit such samples with given frequency to a central server, where we could aggregate them and build train graphs to profile the application running in production. Nothing of the sorts exists for PHP-FPM, and most existing profilers for it are very good, but they are designed for profiling an individual request while debugging, so they don't worry too much about performance. We needed something with a functionality more similar to what Xenon had. Moreover, HHVM counts execution time according to the wall clock, while PHP only counts time spent in PHP code when deciding to time out a request. So it doesn't count anything that happens in a syscall, like doing a database query. Using wall clock time is a big advantage for multiple reasons. Namely, you can put a hard stop to any web request, avoid long-running database queries from occupying worker slots well after you sent back a timeout error to the user. Given there were no pre-baked solutions to do this, we, or better, Team Starling, developed Eximer, which is a PHP extension that's not only free software, but also packaged in Debian, which offers you wall clock time timeouts, and you can use to produce the nice flame graphs like the one here on the right. As you can see, it was a long and windy migration, right? With a lot of moving parts and quite some engineering work needed. So one would think we would have had enough of dangerous migrations with a lot of engineering open questions, right? And instead, we chose to migrate our whole 19 years old LAMP monolith to Kubernetes. Now, the problem is that this feels like a lot like trying to fit the proverbial square peg in a round hole. For instance, how can we fit our current MediaWiki installation in production, which amounts to 32 gigabytes of PHP files on disk, into a containerized environment? On the other hand, we, at this point, have significant experience running Kubernetes at scale. Our Kubernetes clusters that serve basically all of our microservices respond to about 30,000 requests per second. And we think that the effort of moving MediaWiki will be worth it. Specifically, adapting our square peg will force us to repay a good chunk of the dustiest tech debt that we've accumulated over the years. And while at the moment we have more things that we don't know than things that we know, we definitely know what we expect to gain from this transition, which is the ability to scale up and down workloads as we see fit, a modern deployment system and execution environment, and most importantly, a more pleasant experience for developers who will be able to use the same versions of all software we use in production in a consistent way.
Summing up, we had to embark on a complex double-layered migration from PHP 5 to PHP 7 and from HHVM to PHP-FPM. As SREs, we didn't deal with the code changes that much, but rather with rolling out PHP-FPM to production. We set a measurable goal and we did our best to come up with the tools to help us meet it. And knowing that benchmarking can only take us as far, we had to test in production, each time using the techniques and the tools that will serve us best. Because time was of the essence, we tried to choose wisely which battles we could fight and which we should walk away from. And after almost a year of having our production split in two, when the PHP 7 part became manageable, we went ahead and completed the migration. What we can say is that no migration is perfect, mistakes will happen, rollbacks will happen, tasks will fall behind, and morale will have its ups and its downs. But once you're done, you're ready for your next migration because that's what SREs do. Lastly, thank you all for testing encyclopedias in production, and thank you for reading, editing, and loving Wikipedia.